Okay, thank you very much everyone for being here with us. And thank you very much for the MCs for such a wonderful introduction. So our journey today starts here. Okay? This is the Nobel Prize of 2020 that was awarded for the discovery and for understanding of the black holes. So what are black holes? So half of the Nobel Prize was given to the understanding of black holes. And gravity, you can understand that as curvature of space-time. Here you can see the Earth curving space-time around it. And when you have another mass, let's say the moon, it naturally follows the curvature that the Earth produces. And that's what we call gravity. But now imagine we take a lot of mass and we condense it into a single point. What happens then? It pretty much punctures space-time. And that's what we understand to be a black hole. Now, the other half of the equation, the other half of the Nobel Prize, was given for the actual discovery for the black hole at the center of our galaxy. So here we can see actually how this discovery was done. Here you can see, over time, we're tracing stars right at the center of our Milky Way. And we can see all the objects moving around something very massive. But there's no light coming from that area. And if we think about it, if we calculate how much mass should have been there, then we arrive at this astonishing number of 1,000,000 times heavier than our own sun. Yet it doesn't emit light. And that's our first evidence for the existence of a black hole. Now, recently, you may have seen this picture in the news. This was the first picture taken of a black hole. Now, it may sound as strange, right? It's a black hole. How can you take a picture of a black hole? Well, we didn't, in fact, actually took a picture of the black hole, but instead, we actually took a picture of the shadow of a black hole. So here you can see an animation which shows this concept. You can see light rays going around and starting to bend from behind a black hole. And all the light that then is bended towards our way, we can see it. But of course, at the actual black hole, it's black. We can't see anything. And so that's how we end up arriving with an image like this, where you can see the ring and something black in the middle. So black holes are something that we have a fair confidence in its existence. And these are mystical things that we've kind of captured our imagination ever since Einstein theoretically came up with this concept that a black hole must exist. But how are they formed? How can we form a black hole that is more than 1,000,000 times heavier than our own sun? And what I want to do today is actually guide you through the process and show you some of our current understanding in terms of simulations, right? Just our understanding of what happens. But I'm going to do something extra as well. I'm going to also give you an audio tour of how this happens. And I'll explain how this works. Okay, now let's start at the very beginning, where we have dense dust everywhere in the universe. And through the process of gravity, it attracts more and attracts more. And you get a bigger and bigger cluster of dust. And at some point, this creates so much pressure, right? And you add so much more mass to it that the star turns on and starts emitting light. And that's how we create a star. And the star then continues to burn up its fuel, right? Its hydrogen, its helium, and so on, until at some point it burns up all its fuel, it can no longer sustain itself, and it goes what we call supernova. It explodes. It sheds away its shell and then leaves behind something that is only a remnant, only a tiny fraction of its mass. Now, it can either, depending on the size, leave behind what we know to be a neutron star, which is just a big object, about 10 kilometers, but which has the mass of an entire sun condensed into it, which is almost like a single atom. Or, if the star is even heavier, it could even collapse into what we know a black hole. And the result of this process gives us a black hole that's about several times the mass of the sun. But again, we're still not there at the millions of times of the sun. Now, this process of a supernova has actually been observed. And this is actually an animation where you can kind of zoom in, you can pan in on one of the brightest events that happened in our night sky, which was a supernova in 1987. And what we can see nowadays, if we point our telescopes to it, is its remnant, what we call a nebula, right? So its mass that it shed in this big explosion is what we can actually observe now. And it actually makes for beautiful imagery. But still, okay, we want to go to the millions of solar masses. How do we get there? Now, to understand this process better, we actually need to turn to another Nobel Prize, which was given in 2017. And these three gentlemen got it for the discovery of gravitational waves. And let me explain to you what gravitational waves are. So gravitational waves are distortions in space-time that travel at the speed of light. And a distortion of space-time is actually just the changing of length. It's a compression of space-time. And you can see a vastly exaggerated image here, where you can see the Earth being completely distorted by a gravitational wave. Now, these actual distortions are very, very small, and they actually need to be picked up by kilometer-sized instruments that we've built. And this is an example in the US called LIGO, where there's a 4-kilometer machine that we need to pick up these tiny ripples in space-time. And the way this happens is that there's actually a laser being shot. Oops. There's a laser being shot at a mirror, and it bounces back, and then the whole system, is locked in. But when there's a gravitational wave compressing space, you can see a flickering of this laser, of the laser output. And that gives us, the image of a black hole. But better yet, I should actually call it sounds. These ripples actually cause the disturbance in the laser, which we can turn into sound. And that's something that I wanted to do today with you. So I don't only want to show you the process of what happens when we form black holes, but I also want to give you the audio sense of what it sounds like for black holes to be born. So this is the first example. Right? I talked about a supernova producing neutron stars and black holes. Now, first what I'm going to show you is a simulation of how an explosion actually occurs. And you can kind of see this rumbling, this kind of, mess going on, and then at some point, it starts to wiggle, and then it will free itself. Now, let me play the sound, the gravitational wave associated with this. You can hear vague rumbling. It's kind of gradual. It's almost like noise. Now, even in this process, we can actually look at the formation of what happens inside in that process, in the star. And so this is a different example where, in this case, I'm showing the creation of a compact object, phase transition. And you can kind of see, suddenly there's this change, big change, and there's a shock wave being sent out. And then the rest of the star explodes. And again, let me show you what it sounds like in gravitational waves. So you could hear the same rumble that started in the beginning, but suddenly there's big poop, and then a fade off. And this is, for example, a way that we can figure out what was produced in this explosion. Was it a neutron star? Was it a black hole? Now, upon creation, we can still continue to listen to the sound. So first, what I'm going to show you is how does a neutron star sound? Right? Neutron stars have their own characteristic sounds. And so first, again, I'm going to show you the oscillation of a neutron star. And you can kind of see this neutron star rotating around, and you can see the mass being flown around. Now again, the sound of a neutron star. Okay, you can hear this continuous kind of pitch, but then it slowly fades over time. And a neutron star is stable, so you can hear this continuous sound. Now, what about a black hole? Black holes are very, very stiff. Right? They're the most extreme objects that we have in the universe. How does that sound? So what you hear is a very faint blip. It's just a blip, bloop, and it's gone. It's pretty much a single blip, and then because the black hole is so stiff, all the sound, all the gravitational waves is immediately damped. Okay, now to the central question again. We know how to create black holes that are several times the mass of the sun. And we've seen black holes that are a million times heavier than the sun. But how do we get from one place to the other? And that's actually what we call a process where we want to see if we can find so-called intermediate mass black holes. The black holes that are in between several times the mass of the sun and millions times heavier than the sun. Now, we don't necessarily know how this process happens, but we did get clues. Now, the first clue comes from the actual discovery, the first discovery of gravitational waves. And what we saw there was what we call a collision of black holes. Okay, so here you can indeed see two black holes orbiting each other. And this process emits gravitational waves so that the object gets closer and closer, radiates ever more gravitational waves until at some point it collides and forms a single black hole. Beautiful process. So this is actually an image that you would have seen if you were able to get close enough and see the background stars behind it. Now, black holes are too far away, and especially too far away for us to see a process like this happen. But it doesn't mean that we can't understand this process. And in fact, what I want to now show you was the first sound recorded from exactly this process, the collision of two black holes. Okay? Take a listen. So what you just heard was first time you heard it in normal speed, and if you got good ears, you would hear a faint blip. And the second time, we kind of increased the frequency so you can actually hear it, and you can hear this beautiful chirp. The amplitude and the frequency, right? The loudness and the pitch going up as the two objects get closer and collide to form a single black hole. So now we have a process where we take two lighter black holes and form a heavier black hole. Right? This is our first way into making ever more heavy black holes. Now, to highlight the process of how we understand how massive the black holes were, I'm going to play you now the same sound, but from two different collisions. One heavier and one lighter. And I want to show you how that sounds. Okay? So even, especially if you're musically trained and you're able to hear the difference in the pitches and also how the pitch evolved, how it ramps up, that's how we scientists can understand how heavy were the black holes and what end product did they make after their collision. Now, that by itself is great, right? We now have a firm grasp of how we can make out of lighter black holes somewhat heavier black holes. And our way towards an intermediate mass black hole actually came in 2019 when we saw a merger. Again, this is something that I just showed you before, right? There's just two black holes orbiting each other, colliding, forming a heavier black hole. Now that by itself isn't very special anymore in 2019, but what was special is the mass that this collision had. And the mass indeed here was that fell into this intermediate mass black hole region. Now, to give you the sound, I want to play to you the sound. Now, what you heard again is just a faint blip. Right? It's a very short blip. I would always call it a bark rather than a chirp. And just because of that shortness and that burst of energy, that burst of sound, we can infer that this black hole was actually something that was in, this so-called intermediate mass black hole region. Here we can see all the black holes that LIGO has found over the years, and you can see highlighted the one that I just talked about, the one that pushed us over this region where we're no longer talking about stellar mass black holes, but now we're talking about intermediate mass black holes. So indeed, we're actually going towards finding ever heavier black holes and on our way to discover how we can go from light black holes that come from the process of supernovae all the way to seeing black holes that are of the size or the mass that we found in the center of our galaxy. So indeed, right, we now are, with these modern tools, with these modern scientific tools, we're now getting towards mapping out the process of the birth and rebirth of black holes that have such a fundamental importance in our whole evolution and everything we see around us. Thank you.